Hi, I'm Paul. We're doing Leetcode must know interview questions. Today's challenge is find peak element. This is this is under the binary search category, and it's rated medium because there's kind of a twist. It's not just a binary search. So a peak element is an element that is strictly greater than its neighbors. We'll look at an example or two. Given a zero-indexed integer array, nums, find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. You may imagine or assume, I guess, that nums at -1 equals nums at n equals negative infinity. In other words, everything outside the array is negative infinity. An element is always considered to be strictly greater than a neighbor that is outside the array. So the first element would be considered greater than the element to its left. Okay, now there is no element to its left, but anyway, you can imagine that as it says, and similarly, the last element in the array would be considered greater than the imaginary element to its right. Okay, you must write an algorithm that runs in O log n time. All right. Let's see. So in this example, a peak element is 3 because 3 is greater than the element on either side. It's greater than 2. It's also greater than 1. In this one, there's 2 peak elements. 2 is greater than the 1s on each side, and 6 is greater than 5. 6 is also greater than 4. All right. How can we make this work as a binary search? Okay, let me get a pen. Okay. So the variables that we need, we can call them low, which is originally 0. We will have one called high. On this example, there are 1, 2, 3, 4, 5, 6, 7 elements, so high would be 6, and mid. Now mid is low plus high divided by 2, so 3. All right, so the first element that we look at is at index 3, 0, 1, 2, 3. That's right here. Now that happens to be a 3. We also look at the value to the right of 3, which in this case is 5. Now, if that element is greater than the midpoint, then there's going to be a peak element to the right of the midpoint. How do we know that? Well, it's kind of a you can see it, kind of process of elimination. Okay, so the 5 is greater than the 3. What about the next number? Well, if the next number were less than 5, then 5 would be a peak element. In this case, it's not. It's greater than 5. So if the element to the right of that is less than 6, then 6 is a peak element, and it is. But it doesn't have to be. It could be greater than 6. It could be 7. But because we are assuming that everything out, in this area here is negative infinity, if that were greater than 6, then that would be the peak element because it would be greater than 6. It would also be greater than whatever is to the left. If this number to the right of the midpoint is lower than the midpoint, there's no guarantee that there's going to be a peak element to the right. Those numbers to the right, for example, could be 2, 1, 0, no peak element. So because, as I understand the problem, we're guaranteed that there is a peak element, then when we hit a midpoint, look at the element to the right, and if it's greater, then we are using the top half of the search space. Otherwise, we're using the bottom half of the search space. Anyway, so to see how this would proceed, we look at this. We see that this is higher. So in that case, we've got to reset the indexes. Or the index. We got to set low to mid plus 1. All right. And we'll get rid of that. Mid plus 1. All right. So, I'm sorry. Mid. Yeah. Okay, good. Mid plus 1 is not 1. Mid plus 1 is 4. All right. Now we need a new midpoint. 4 plus 6 is 10. Divided by 2 is 5. All right. So we are now at a new midpoint. It's right here. 6. Is the element to the right greater? It isn't. So we are throwing out the top half, or the right half of the search space. So high becomes mid, right? Now, add low and high. 4 plus 5 is 9. Divided by 2. Integer division is, let's see, 4 plus 5 is 4. 4. Okay, so we'll look at index 4, and that is, where's that? That is here. Is the element to the right greater? Yes. So we adjust the indexes. We throw out the left-hand side of the search space, and we increment low. It becomes mid plus 1. All right. Now, as you probably know, once low is no longer greater than high, the while loop ends. We're done. And low then becomes the index of the peak element. In this case, the index of the peak element is 5, which is this number right here, the 6, and that's correct. So let's see what an implementation of this would look like. All right, I'm going to look back at the first easy level challenge in this group, which was just a basic binary search, because really this is just a basic binary search with the addition of recognizing how you can use that comparison of the mid element to the element to the right of the mid element. All right, so let's plug this in. This will be the same. Low is 0. High, actually, in order to make this work, we need num's length minus 1. So that in our example would be 0 and 6. We can say while low is less than high, mid equals low plus high divided by 2. All right. If num's mid, now there is no target, but we can say if num's mid is greater than nums at mid plus 1, then we are throwing out, let's see, that one is less. So we are throwing out the top, wait a minute, wait. Yes, we're throwing out the top half of the search space. So high equals mid, right? Else low equals mid plus 1. That's the end of that. And at the end, we return the low index. All right, so again, a basic binary search with an additional comparison. Okay, let's run it. Compile error. What? Turn low. Hold on. Line 16. Do I have that in the right place? I think I do. Let me pause this for a second. Okay, sorry, the copy and paste there. I managed to leave a couple extra brackets in there. Let's try it now. Okay. All right, so there's something else. If that ends, and then the while ends, and then we return. Okay, sorry. Did I take both of those out? I didn't mean to take both of them out. I just want to take one of them out. All right. Now let's try it. Can I move that out of the way? Okay. Run. This should work. I was just closing off the method too soon. All right, so that's accepted. Basic case. And move this back over, and we'll go ahead and submit. Let's see. There are not enough accepted submissions to show data. That always surprises me. But anyway, analyze complexity. What is it supposed to be? Log n, right? Oh, log n. Okay. So that's it. Binary search with a slight twist. That's it for today. Hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.